String time crystals. Presentation for the annual Time Waiver and Healy Scientific Advisory Board Conference, September 2024. By Dr. Hovdank Tadeus. String time crystals and Bose-Einstein condensates as a new state of matter involves three parts: holistic string time crystals theory, string time Bose-Einstein condensates matter, and string time crystals and Bose-Einstein condensate for therapeutic application in quantum feedback. String time crystals. Holistic string time crystals theory. The core concept in string time crystals theory is Bose-Einstein condensate as a large-scale quantum field to activate strings' vibration modes, so that they translate into time crystals. The collective quantum nature in Bose-Einstein condensate might allow it to serve as a large-scale quantum field, through which the strings' vibrations are effectively activated or enhanced, which enables the strings to resonate at frequencies that correspond to particles or states that exhibit time crystalline behavior, where the Hopf bifurcation acts as both the initiator and sustainer of the periodic oscillations. String time crystals. The interplay between string theory and time crystals delves into the assumption that string vibrations could mirror periodic time patterns, akin to those observed in time crystals. This proposal seeks to broaden the traditional particle-focused view of string vibrations, integrating an understanding of intrinsic temporal periodicity. This foundational research could inform further studies across various domains, including Bose-Einstein condensates and their applications in bioresonance therapy. So to begin with, what are time crystals? Time crystals are a state of matter that exhibit periodic changes in their quantum state, breaking time translation symmetry, which means they repeat their structure in time instead of space. While conventional crystals have a repeating spatial arrangement, time crystals show a pattern that oscillates at regular intervals. These oscillations can occur without energy input in a closed system, or they can be driven by an external periodic force in an open system, where the oscillations occur at subharmonic frequencies relative to the driving force. Let's delve into why time crystals are considered a new phase of matter. Unlike traditional phases, time crystals are unique because they can exist in two distinct dynamic states. One is the time crystal phase, where the system shows regular oscillations over time. The other is a stationary phase, where the system remains static, showing no change. This dual ability, this bistable nature, allows time crystals to switch between these two states. This switching depends on external conditions, like changes in driving frequency or coupling strength. Time crystals bifurcation and tricritical point. This switching behavior is often due to a bifurcation in the system's parameters, where the system transitions from one phase to another. The transition between these phases changes nature at a specific point known as the tricritical point. In the time crystal phase, the system exhibits unique quantum behavior, with atoms and light fields becoming collectively entangled, reflecting the non-equilibrium and dynamic nature of this state. Subharmonic frequencies. Subharmonic frequencies in time crystals are fractions of the external driving frequency, reflecting temporal symmetry breaking. This results in a stable, periodic pattern that resists disturbances, maintained by the system's quantum coherence and interactions, showcasing the unique ability of time crystals to remain in a non-equilibrium state. Unveiling the quantum holistic nature of time crystals, bridging classical physics and quantum realities. Time crystals and quantum tunneling both illustrate the unique behaviors possible in quantum mechanics, involving non-equilibrium states, coherence, and symmetry breaking. While time crystals break time translation symmetry to maintain periodic oscillations, quantum tunneling involves breaking through spatial barriers in ways forbidden by classical physics. Understanding these connections deepens our comprehension of quantum systems, where stability, transitions, and coherence all play crucial roles in defining the behavior of matter at the smallest scales. Phase space of a particle on a vibrating mirror. The dynamics of the vibrating mirror system, like subharmonic resonances where a particle oscillates at a fraction of the driving frequency, resemble the subharmonic responses in time crystals. Studying these resonances helps researchers understand the conditions for time crystals to maintain their periodic state and how external driving can cause time translation symmetry breaking. String time crystals order Hamiltonian example. Hamiltonian H at the bifurcation point B, a random log normal distribution of the system's energy fluctuations R log normal E, an imaginary number J, a normal distribution in kelvins phi t, and a random log normal distribution of order R log normal O. Quadratic oscillator. Generalized versions for nonlinear oscillator model considering up to 26 dimensions as an example for non-bifurcation quadratic oscillator. R random elements, C capacitive elements, I field, U field's potential. String time crystals bifurcation nonlinearity problem. Understanding time crystals and their bifurcations requires studying non-equilibrium phases of matter, potentially using techniques from quantum field theory and statistical mechanics. Bifurcation in time crystals is significant because it represents the transition between different temporal phases within a system, revealing the complex dynamics of time translation symmetry breaking. This phenomenon allows time crystals to exhibit multiple distinct periodic behaviors, or temporal orders, under varying conditions, such as changes in external driving fields. Hopf bifurcation. Hopf bifurcation in time crystals is the process by which a system transitions from a non-oscillatory, stationary state to a stable, oscillatory state as parameters are varied, marking the onset of time crystalline behavior. This bifurcation is crucial for understanding how time crystals form and maintain their periodic temporal order, highlighting the interplay between stability, symmetry breaking, and dynamic oscillations in these unique phases of matter. Asymmetric double well potential. An asymmetric double well potential serves as an analogy for time crystals when a bifurcation is present. In this analogy, the two wells represent different states of a system. A bifurcation occurs when a parameter change causes the system to transition from a non-oscillatory state to a periodic state, similar to how time crystals transition from a non-time crystalline state to a time crystalline state, breaking time translation symmetry. Log normal distribution, biquantum realm state. Model time crystals describing a bifurcation quantum oscillator. Figure 2D from Dicapoltsev et al.'s study shows a log normal distribution of the power carried by electromagnetic radiation versus radiation angle, highlighting a strong agreement between analytic calculations and FDTD simulations. This demonstrates the accurate prediction of the log normal emission pattern of light in photonic time crystals, validating both the theoretical approach and simulation methods in capturing the dynamics of light emission influenced by medium modulation.